I was talking about the let's see, over here, the waning crescent. The one last thing I wanted to point out is that's the waning crescent is the phase of the moon that you see early in the morning. If you go out early in the morning, relatively early, and you see, you can even see the moon during daylight. Anyhow, this part, and of course, the waning crescent lasts for about a week, so it's a week between roughly the third quarter and the new moon. Okay, and then of course the new moon occurs again when the moon and the sun are in the same portion of the sky, and of course the cycle starts over again. The cycle takes roughly 29 and a half days to complete, and it just keeps going over and over and over. All right. Here's the reason that we don't see eclipses every single month. Now keep in mind, the moon's shadow is always there, the Earth's shadow is always there. But the thing is, the moon's orbit around the Earth is tilted by roughly 5 degrees, a little more than 5 degrees. And so because of that tilt, in other words, like the moon doesn't go like exactly over the equator. It is tilted by about 5 degrees. Anyhow, because of that tilt, the moon's shadow doesn't always hit the Earth. Again, it's always there. But now, when it does touch the Earth, here's the other thing. I should mention this as well. The moon, when it orbits the Earth, it doesn't orbit the Earth from the same distance, right? It varies its distance slightly, just like the Earth going around the Sun. The Earth gets a little closer to the Sun, a little further from the Sun. In fact, the Earth is closest to the Sun in January, it turns out. Which, again, if you go back to why it's hot in the summer, it has to do with the tilt of the Earth, not when it's close, not when the Earth is closest. But anyhow, the moon gets closer to the Earth, a little bit closer to the Earth, a little bit further from the Earth. So there are actually times when the Earth's shadow lines up with the Earth, but it doesn't quite touch the Earth because the moon is too far. And then, of course, if the moon is a little bit closer, then this shadow is larger. And so anyhow, when the moon's shadow hits the Earth, that's called a solar eclipse. And you have to be just in the right spot for that to happen. Most of the Earth, of course, most of the surface of the Earth is covered with water, and so a lot of these solar eclipses occur over oceans. Now, and of course, think about what the phase of the moon has to be, right? This can only occur during a new moon, right? Now, of course, when the moon is full, that means that there's 180 degrees between the moon and the sun. And now, usually, of course, the moon does not pass through the Earth's shadow because, of course, the moon's orbit is tilted by about 5 degrees. But there are times when the moon does pass through the Earth's shadow, and that's called a lunar eclipse, right? And the nice thing about a lunar eclipse is you just have to be in the portion of the Earth where it's nighttime, right, for you to see a lunar eclipse. I mean, sometimes you have to wait until the portion of the Earth that you're in rotates into the nighttime for you to see this. But this lasts a good long time, several hours. And the one thing is I should mention about lunar eclipses is that the moon is not completely dark during this, even though it's in the Earth's shadow. The reason that it's not completely dark is because of the Earth. The Earth, of course, has an atmosphere, that extends roughly 100 miles above the surface. And so what happens is, just like a lens, or just like, light passing through a lens, the sun's light that passes through the Earth's atmosphere gets bent, and in fact, the red light gets bent the most, and so the moon will appear slightly reddish, even during a lunar eclipse. All right. Let's see. And of course, there's partial eclipses, because, the moon is moving, as I said, closer and further from the Earth. All right. And this is showing like the annular eclipse as well. When you get just a portion of the sun blocked out during a solar eclipse. All right. Anyhow, let's move on from that. This is just showing this tilt of the moon's orbit. This is why you don't get eclipses every single month. And let's talk about and I'm going to do a separate video where we actually do some of the math, but this is the beginning of what the parallax method of finding distances in space. All right, so it started with the Earth and our knowledge of trigonometry. Actually, just basic geometry. You don't even need trigonometry to do this. Although trigonometry does help as well. So suppose you're trying to measure the distance to some distant tree, let's say, and there's a river in between, and you don't have long enough, tape or something like that that's going to measure that distance. The way that you would do that is called triangulation, and this has been used for millennia, or so thousands of years. Humans have been using this method. The way that we do it is you establish what's called a baseline. And it turns out it's easier to line up one edge of the baseline so that it's at 90 degrees with respect to the object that you're looking at. So like, for example, for this tree right here, it's exactly 90 degrees with respect to the baseline. So the baseline is a distance that you can measure directly. You have to physically measure this distance, right? So from A to B. So you physically measure that. And then what you measure is the angle between the baseline and the object that you're trying to find the distance to, right? So you measure this angle very, very carefully. Usually you use a little telescope. If you ever see surveyors at the side of the road with their little telescopes, that's exactly what they're doing. They're using this ancient method of triangulation. All right. So let's see, what else did I want to say about this? So this is stuff that's done on Earth. Done long before there was satellite navigation and so forth, that we enjoy quite. I enjoy it as well as anybody else. That you just look at your cell phone and you know exactly, pretty close to exactly where you are on the Earth. All right. So one of the things that we found is to find distances to relatively close objects like the moon, for example, or other planets within our solar system. You can use the baseline of the Earth itself. Like if you were to measure, what the position of some object like the moon, or some portion of the moon, actually, not the entire moon, but you'd measure some portion of the moon with respect to the distant stars, and then measure it half a day later, and measure the distance to the moon to some distant stars, and measure that angle very, very carefully. The angle between between the two points is called the parallax, and you can see a parallax. It's actually really, really simple, and I'll show this in the classroom or I'll have the people that are sitting in the class will get to see this. If you hold your finger at arm's length and then close one eye, and then you look at some distant object like the wall or something like that with the one eye, and then what you do is close the one eye that's open and simultaneously open the other eye, you'll see your finger shift slightly. And that shift is what's called parallax, right? And the reason that there's a shift is because your eyes are roughly 3 centimeters apart. The average human's eyes are about 3 centimeters apart, and so that tiny shift that you see is what's called a parallax, because you're looking at your finger from 2 different points of view, roughly 3 centimeters apart, and so you see that shift. All right. So this idea of using parallax and triangulation was actually used long ago by a guy named Aristophanes. He was he was a Greek. He actually lived in Alexandria, Egypt. He's associated with the Greek culture. Anyhow. He was actually the chief librarian, or the head librarian, in the great library of Alexandria in the ancient world, and he ran across a scroll that reported that there was a city, somewhere to the south. Its name was Ch1, and there was a certain day of the year. It was right around June 21st. That in Ch1, an object like an obelisk or something like that that is pointed straight up and down, or a well, like if you were to look at a well in Ch1 on June 21st, or at noon on June 21st, you would see no shadow in the well, or you would see no shadow from the obelisk. And so this guy Aristophanes, he was an absolute brilliant mathematician. He was a brilliant individual. He realized that if you knew the distance between Alexandria and Ch1, and on that same day in Alexandria, if you were to measure the angle of the shadow at noon, on June 21st, he actually measured that angle. It turned out it was about about a little more than 7 degrees. If you were to measure that angle, and if you knew the distance between Alexandria and Ch1, and Ch1 is right on the Nile River. It's in Egypt. And so if you knew what that distance was, you would know. You could actually use geometry and those measurements to measure the circumference of the Earth. And in fact, he didn't actually make the trip himself. He actually paid somebody to walk to Ch1 and then walk back. I always think that he probably paid the guy half the money now and then half the money if you come back, because why would the guy even come back if he got all the money to begin with? Anyhow, so the guy does come back. He reports the distance from Alexandria to Ch1. Aristophanes actually measured the angle himself, and of course, the rest is history. That is, more than 2,000 years ago, this guy Aristophanes was able to measure to a pretty good accuracy the circumference of the planet Earth by using, angles and distance measurements. All right, so pretty amazing. All right, so this is just showing you how he did it. All right. I will go into some of this stuff. This stuff in a little bit more detail when we do the math. So this is really just a summary. Let's see, how much time do I have? Oh, it's almost over. Very good. All right, so this is the chapter 1. All right, very